Hi everyone, today we're going to learn about graphing linear inequalities. Now, we've already know how to graph linear equations. What we're focusing on now are the inequalities. That's instead of things like y equals 2x plus 1, we might have y is greater than 2x plus 1, or y is less than or equal to 2x plus 1. But before we get into those, let's just do a quick review of graphing linear equations so everyone's on the same page. All right, so we're going to just do slope-intercept form here. This equation, y equals 2x plus 1, is already in slope-intercept form. So remember that this is our y-intercept, and that's where you're going to start. That's your starting point. So it crosses the y-axis at 1. Put a point there. This is your slope, 2. So 2 is a rise of 2 and a run of 1. So from one point to the other, we rise 2 and run 1. So if I'm starting at the y-intercept, I go up 2 over 1, up 2 over 1. And I can do that over and over again, and you should do it more than one time. If you run out of room, you can always go backwards. So instead of up and to the right, we can go down and to the left, because that's like a -2 and a -1 for your rise and run, going down 2 and to the left 1. Which is still a +2 slope. So if you're going to go backwards, make sure you change both directions for the vertical and the horizontal. So just to reiterate what this means is this line is showing you all the places where the y value is equal to 2 times the x value plus 1. To put it in perspective, let's take a random point. If we look at this point right here, that point is 2, 1, 2, 3, 4, 5. My x is 2, my y is 5. Keep in mind, this equation says that y should be the same as 2 times x plus 1. Well, if I take my x and I do 2 times x plus 1, that gives me the y value. There's an infinite number of xy points that fit this description. That's why we draw a line with arrows showing that this line continues. There's an infinite number of x's and y's that will work in this equation, and this line is showing all of them where they're equal. Now to move on to an actual inequality, which is what we're doing next. Here's a good example. We're going to do 3 examples. This is the first one. Instead of being just y equals x minus 1, we have y is greater than x minus 1. So we can start off the same way we start off the way it would be if it were an actual equation, like if it were y equals x minus 1, because that is part of the solution set. So remember, y could equal x minus 1, and all those values where y equals x minus 1 are part of the solution set. Think about a t-table. If I pick some random points, for instance, if x were 0, then in order for this equation to work, where they're actually equal, y would have to be -1. All right, if x were 1, then in order to make this equation equal, y would have to be 1 minus 1, 0. Those are all points on the line. We can still graph it like it's in slope-intercept form, just like anything else. We know that -1 is our y-intercept. We found it using a t-table also. So that's where we start. And then the slope is 1. There's an imaginary 1 in front of that x. So that means go up 1 over 1. Up 1 over 1. And this line shows you all the points where y is equal to x minus 1. Whatever the y value is of every one of these points, for instance, this point right here is 3, 2. Notice that the y value is the same as x minus 1. If you take the x value, subtract 1, that gives you the y value. This line shows you all of those points where that is true. But instead of an actual equation, if it were an equation, we'd be done and we would just show this line and say, hey, here's all the points where y equals x minus 1. But we have this symbol, and it says y is greater than or equal to x minus 1. So what does that mean? If we go back to our t-table where x was 0, so we said in order for them to be equal, if x were 0, y would have to be exactly -1 to make it equal, and that does work. But this inequality doesn't say that y has to be equal to x minus 1. This inequality says that y is allowed to be anything equal to or greater than x minus 1. So if x were 0, like here, y could equal -1, but it could also be anything greater than -1. So having a 0 for the x and a 0 for the y would also work, because if I solve that equation, y is still going to be greater than or equal to x minus 1. Let's look at some other examples. I'm going to erase some of this to kind of clean up this. If x is 0, y just has to be equal to -1 or anything greater than. So y could be -1, y could be 0, y could be 1. Anything bigger than that, the list goes on and on and on. So there's a lot more values when we say y is anything greater than or equal to -1. If x were 1, let's take that example. We already said right here that if x is 1, in order for them to be equal, well, y would have to be 0, and that is one solution. But again, it doesn't have to be exactly equal. If x is 1, yes, y can equal 0, but y could also be anything bigger than 0. So it could be 1. That's a valid solution when x is 1 and y could be 1. If x were 1, y could be 2. If x were 1, y could be 3. All of these points are valid solutions to the inequality y is greater than or equal to x minus 1. And I know this is kind of a lengthy explanation for one problem, but I want you to understand why we do what we do. The only way to show this on a graph, there's so many points besides just the ones on this line. So if I were to plot these points, and I'm looking at 0, 0, which is already, 0, -1 is already plotted. If I go back to 0, 0, that's this point right here. If I look at this point, 0, 1, that's this point right here. 0, 2 is this point right here, 0, 3. And I could keep going, and all of these values for y that are bigger than 0, -1, all of these points are valid solutions. Looking at the 1, we already plotted 1, 0 because that's where they're equal, that's the line, but remember y could be anything bigger than that. So y could be 1 when x is 1. Okay, when x is 1, y could be 2, or 3, or 4, or 5, because y just has to be anything bigger than x minus 1. The same would happen for when x is 2. It could be any of these points. So to show all the values that work, it's basically anything at this line or above it, because that's where the y values are greater than x minus 1. So to show that, what we do is we draw our line, and we usually want to draw it as long as we can all the way across the graph, and then we simply shade everything either above or below the line. So the line itself represents everything where y is equal to x minus 1. The shading shows you also that y can be anything equal to or greater than x minus 1. So the gist of this is we're going to graph the line like normal, no matter what, show where they're equal, and then we're going to shade either above or below it to show that y could actually be that line or anything above it or anything below it. We would shade below the line if it said y is less than or equal to something, because then y would have to be smaller numbers than where that line is. So let's do 2 more examples so we can get the hang of this. So this example is different for a couple of reasons. One is it's less than instead of greater than. Also, it doesn't say equal to, so I'll show you how to deal with that. Regardless of what symbol you have, you start off by graphing the line as if it were equal to. That's still our starting point. Even though it's not allowed to be equal to in this one, we still want to start with that, and I'll show you what we do a little differently. So I'm going to graph this line where it's equal like I normally would. 3 is my y-intercept, so I'm going to start at 3 on the y-axis. My slope is -2. That means go down 2 over 1. and I'm going to do several points because we have to make this line really long so that we can see the entire graph and then connect those points. So this right here is the graph of the line y equals negative 2x plus 3. It's showing you all the points where the y value for that point is equal to negative 2 times the x plus 3. Now, we're not allowed to actually be equal to. So instead, we're less than. And if you remember anything from solving inequalities way back when you had less than or greater than symbols and you were graphing answers on a number line, so for instance, you had x is greater than 3 when you were solving equations, or you just had to graph everything greater than 3, you would use an open circle to show that it could go up to 3 but couldn't actually include 3. And then you would draw your arrow either going to the right or left. Going to the right says x is bigger than 3. It's kind of similar for graphs of inequality lines. Instead of an open circle or a closed circle, what we're going to use, let me put this back, is as opposed to using a solid line like I did on that last example, that should be there, I'm going to use a dotted line. So this dotted line kind of acts like your open circle. The dotted line is going to be used when you have the greater than or the less than symbol without the equal to. We use the solid lines like we did in the last example when it could be equal to. It's greater than or equal to or less than or equal to for our symbol. So we just need to remember if it's one of these two symbols, we use a dotted line. Okay. Now, the other thing that's different about this is that we don't have an equal sign. We have a less than sign. It's not greater than, sorry, like the last time. It's less than. So that means the y value is allowed to be close to anything equal to, not exactly, but pretty close to anything less equal to negative 2x plus 6. That's the line. Or smaller. So what you have to think to yourself is, where are the smaller y values? And a good place to start is at wherever it crosses the y-axis at 0. Pick this point where it crosses the y-axis and think, where are the smaller y values? Are they above this line or below this line? Well, the smaller y values go down because it works like a thermometer. It gets smaller as you go down. So what we need to show is that the y value could be at these points plus all the points where the y is smaller than that. So we're shading under the line. All of these values at the line and under it, meaning going straight down from a point on the line. All of those are values where the y is less than negative 2x plus 3. So we graph the line just like it was an equal sign, and then we shade either above or below. If y is less than, we shade below the line. If y is greater than, like in the first example, we go up from the line. So we put our pencil on a point and go up. It's usually easy to put your pencil on the y-intercept and then draw a line going up or down. That's the side you shade. You should be shading half the graph all the time. Not exactly half, but either above or below. All right. So let's do one more example. This example is a little bit trickier just because we have to isolate y. It's not in slope-intercept form, but you should be familiar with doing this. We just have to be careful with inequalities because there's one little catch. But we started off the same way. We got to get y by itself. So we're going to subtract 3x from both sides. To start off, these cancel. I have negative 4y is less than or equal to, I'm going to put the negative 3x first and the plus 4 because that's more like slope-intercept form. Still not done. I have to divide before I have y by itself. So I'm going to divide everything by negative 4. And this is where it gets a little tricky. You have to remember, hopefully you remember this from previous years, when you divide by a negative, if this number right here that you're dividing everything by is negative, you have to flip the inequality sign. What that means is we're going to change that less than or greater than to a less than or equal to, to a greater than or equal to. And then that ends up being positive 3/4 x, and that's a minus 1. So we can't forget to flip the sign if we divide by a negative number. All right, now we're going to go ahead and graph this. graph it as if it were just plain old y equals 3/4 x minus 1. Start with your y-intercept at -1. Slope is 3/4, so we go up 3/4. Go do that a few times. Up 3/4. We can go backwards too. And then think, before you connect the dots, do we need a solid line or a filled in line? Because it can be equal to, we use a solid line all the way across the graph. If that didn't have the equal to line, we'd use a dotted line. All right, then you got to think, which side do we shade? We're either going to shade everything above the line or everything below the line. Well, because y is bigger than the line, or equal to, we shade up. That means, easiest thing, put your pencil on the y-intercept, draw an arrow where the y values are greater than that. That means going up. So all the points that are above the line are going to be part of our solution set, and we show that by shading the whole section above the line. All right, so in short, you're basically going to graph the line and slope-intercept form like normal, choose a dotted line or a solid line, and then shade above or below that line to show all the values of a linear inequality.